So today I'm going to talk about our recent experience about developing a method jointly with MIT in US, where we have really developed a method that certifies that your system is really secure. So how we are going to see it, let me give you some perspective from the industry. So currently, if you ask an industry, can I afford to certify the security and reliability of my computing system, whatever I have developed? Certify here, I precisely mean a mathematical proof that assures that your system is reliable and secure. It's not the certification which we usually are used to of doing, like ISO certification, but it's really a certificate which is a mathematical proof. Probably the answer will be no. So why? There are many reasons, but few of them are because even if I make mistake, no problem about that. Why? Because I will be notified by the client, I will fix the error, re-release the software, and everything works fine. There is no penalty, right? So there is no regulation either on the other side that whether I have to develop software following certain guidelines. So I do whatever I want to do. I develop my app, even if I'm an undergrad student, even if I'm a high school student, I just put it on the web. I put it in any environment and everything works. Of course, this kind of method requires more cost and time, which doesn't pay off usually with respect to the industry, because industry is competing in developing the solutions as faster as they can. And importantly, they require really different skills that are expensive, because they are not the typical just software development skills, but they are really the skills combined, development skills combined with the mathematical skills. So let's see the recent developments. When I say recent developments, it's really in the last 3 years in different dimensions of the development areas. So one of them is socio-economic. So every one of us is aware about the insider attacks. Marushi is one of the very popular example, where any employee was screwed with his boss, and then he decided to revenge it and eventually exploded the water distribution system. There are stealthy attacks, which we know, which are hard to detect because someone is observing us for a long period of time. And even if we have developed the system which is working correct, still I can have the wrong data on which my system will work. So there is no way to detect that, apparently. Snowden revelations, maybe you are aware of this guy. He just leaked some information from United States Department. And he was in charge of actually maintaining those kind of records, but unfortunately, he leaked the information. Recent US policy for browsing the internet, because ISPs are allowed to share your data with whatever they want without asking you. And now people are in trouble, but that's how the life is. And then the recent dispute between automotive vehicles insurance. So Tesla has developed thousands of automotive vehicles. Other companies have also did the same job. But in order to run them on the road, they need insurance. And the insurance companies are asking the same question as we have. For example, if I go somewhere for my health insurance, the first question I get is, give me your health certificate, so that I know that you are not at least going to die tomorrow. Yeah? So the same question has been asked to the automotive vehicles. We can insure you, but can you provide us the health certificate of your system, the automotive vehicle? And unfortunately, we lack these kind of things at the moment in software industry. All we do is this testing, simulation, and these kind of things, which are definitely not sufficient enough to give an evidence that we will not have any more accident. Then is the parallel things going on in the technological area. So here, let me introduce you these two efforts, which I'm not sure how many of you are aware, but one of them is the CompCert. It's the first commercial certified compiler for C language. So it's out. It's out in the market since 2015. And now you can compile your C program with guarantees that it does not have any security problem, or it does not have any reliability problem. It does whatever you want to do it. So there is a certificate, right? Then there is another effort going on in the United States, which is DeepSec. This is a very joint effort. This has started last year, and it is going to end in 2021. This is a very joint venture, as you can see, between some big universities like MIT, UPenn, Yale, and Princeton, but also they have involved some software companies and hardware companies. So academics and research, software industry and hardware industry, they all are combined to push these methods where we can really assure end-to-end certified software development. I start with my specification, I start proving the things, I start adding the requirements, eventually I get the product. But whatever the product I get, with it, along with that, I will get a proof that this product, what does exactly it do. So this is, I hope we will see more in the later slides. Then there is another dimension which is the legislative. So there are many things also happening at government level. For example, just to give you an example, just in this year, in 2017, more than 42 United States has passed more than 240 cybersecurity related bills. So it's enormous development. Everyone wants now to be secure. So they have passed these regulations. I will show you a little more detail about that. And also on this, at the same time, they are asking that we do not need black box computer systems anymore in our government sector at least. We want systems to be very transparent. And this is because of the audit reason. And fourth thing, which is another very interesting for you maybe, is in the business. So people have already started building these kind of solutions where they can sell. And Rubica is the first ever company which is going to ensure your cyber crimes. So for example, if you want that, okay, maybe my system can be attacked, or my business can be attacked, my family or friends can be attacked, I can ask this company for the cyber crime insurance, and they will give me the insurance up to $1 million US dollars. I mean, they do very basic things at the moment. All they do is they try to back up your system and they try to see what has happened, but still the business is there. They have already started getting money. And the other part is again CompSat, because this is already a business product is there. People are selling it. When one is selling it, of course, we will have the customers. So considering these different developments in the different areas, now let's take a little closer look at the technical and the legislative ones, because otherwise we don't care. So certified compiler about C is really the compiler which gives you at the end a mathematical proof which you can see, and you can show it to anyone in the world to see whether something is written wrong. So it's an open challenge, right? It really makes sure that whatever the source language you give it to input, its optimizations and the compilation at the end does not change anything in it. The meanings of the programs remain the same. So nothing is going to be changed, right? And importantly, it proves, it gives you an assurance that there is no miscompilation issue. So everything is perfectly done. You will have a certificate for that. You do not need to run the system again and again. You do not need to have thousands and millions of tests. You do not need to prepare the tables and these kind of things. Just a mathematical proof is there, which can be checked by any other machine as well. So it's not only that human can check it, but it's also that any machine can check it. The other project, DeepSec, as I already told you, that this is a big venture between academia and the industry from software and hardware together, because they are working for the same goal. And the goal is the following. At the moment, we have this software engineering paradigm where we have the modules which are programs, which are software, which are functions, and they are linked with the interfaces, some input and some output interfaces. They are going to change this paradigm to software verification paradigm, where instead of modules, we will have the proof that why something does work. Why? Here we have implementation, we have what do we do, right? Here we will have why does it do, right? And then instead of interfaces, we will have the specification, which will be a contract. When you are going to use my software, you guarantee me that something will not go wrong, then I will guarantee you that the result, whatever I produce, will be correct according to your requirements. So this is the list of some tools which are going to be the outcome. By the way, already these tools are out. These tools are available. And these tools really assure you they are operating system which are verified operating system. You know everything about the operating system, right? You also know everything about the hardware circuits in Kami. You also know everything about the server. And there are many more things, and one of them is this verified software tool chain, where you can there is a combination of all these tools, starting from high level of specification to the end of the implementation, which is hardware circuits. So it really covers the full stack of the software development. Now from the legislative developments, just to give you an idea that what are the bills which were passed in this year. So they are already effective, by the way, in New York and Colorado State since March and June. So just look at it, for example, audit trails. They required that you show us the proof that audit systems showing how they detect cyber crime events. At the moment, if I ask you, do you have an idea how do we detect the cyber event? No idea until I'm a victim. Yeah. So they really are looking into the process. They are really looking at your tools which you are using to detect your cyber crime. Because otherwise you cannot just claim that, yeah, I'm perfectly fine, I'm secure. No, it's not the case. They really ask you for a proof. And when they say proof, it's really the strongest evidence in its form. Right? It's not just an empirical one. I cannot say I executed 2,000 tests and out of them 1,900 passed. Yeah, but still 100 failed. So there is no assurance. They really are looking into the process. And as you see further, they are also asking for the secure development process so that everything when you are developed, for example, one software developer has developed module A, the other has developed module B, we really want to make sure that none of them has introduced any vulnerability in the software. We really need to use these kind of methods. So this is from the legislative point of view, and this all brings us to now the new requirements of the future system. And the requirements are the following. We really want to develop the certified computing systems. Certified. Again, certified means the mathematical proof affiliated. So, such that we really support the audit against regulations, against laws, against policies, because there are many things. I have my organization, I have my policies, there are certain laws under which I have to work, but there are certain regulations which I have to adhere. So there are many things around. I have to really make sure that whatever I am running, can I show that my software is compliant with all these things which it has to? This is what we need now. We also need the formally assurance of the reliability and security. We do not need just testing and simulation. We really need the proofs. We really need the mathematical proofs where people can say, yeah, your software is really secure. Why? Because this is the argument. And the argument is the logical argument. Of course, these have to be understandable by the human and at the same time by the machine, because we still believe that as long as the human is in the loop, things may go wrong. So you should be able in principle to verify the same software by any other machine to whom you trust. Of course, the system should be self-organized and resilient, because nowadays the infrastructure has been very complex. Systems are connecting on the fly in the internet like cloud computing and some edge computing ways. So we really want to make sure that whatever the components communicate with each other, we really know at some point if something goes wrong, and we should be able to recover from that if something goes wrong, even if there is an attack or if there is some error. So for us, program analysis and verification is the key to these requirements and challenges. This is what we are going to use. And now, if I tell you that the future industry trend will be, can I afford not to certify security and reliability of my software? Of course, the answer will be no. I should. Why? Because otherwise I will have unaffordable penalty, because there is a regulation which I didn't follow. And then I'm unable to sell my software anymore. Yeah, because there are other companies who are doing everything certified. So I will not be able to do it. And of course, it is going to eventually affect the revenue of my business, because I will lose the customers, because my software has lost the credibility. And you have seen recently the Volkswagen, for example, incident of their diesel and carbon dioxide emission testing system. So what are the challenges which we are going to address in this method? As every one of us know that nowadays these modern computing systems are very diverse. They really are combination of computation, physics, biology, chemistry, and many other domains. They also include the algorithms from IT. They need logic from mathematics. They need control theories. There are many other domains, scientific domains, which are involved. But also on the other hand, there are some operational domains which are involved, which are interdisciplinary. For example, economics and energy are working together. Medicine and energy is working together, and law is there. So there are many things around. So now my software is no more isolated. My software has to interact with all these domains, and all these domains have their own boundaries, their own rules, their own regulations, right? So systems have become overly complex and hybrid. They are reliable, they should be reliable and secure when they are interacting with each other, because otherwise I cannot secure the medicine world with my law, and I, on the other hand, the same way. So we really are looking forward to develop the system which are self-aware and self-organized, which means they should know what they are trying to do. So system should be self-aware. System should itself know what it is going to do, because otherwise there is no chance to protect it against anything, right? So how do we do it? In order to do that, we put everything into the context that we are given a system design, we are given a system implementation, we are giving a whatever you give me system model. Then I want to show you that this design or model and its execution. So we are talking about two times. So the static version and then its execution, because when you are developing something, you are everything is happening in the secure environment, but when you execute it, everything is in an unknown environment, so anything can happen. We want to make sure that at both stages the software is secure. And the current solutions, as every one of us knows, are testing and simulation, but unfortunately there are many problems. Either they are random or they are highly random. There is no way to have a good test, there is no way to have a good simulation. And as Digestra said, they can tell you that there is a bug, but they cannot prove you that you are free of bugs, right? So there are some other methods which are these standardization organizations like ISO, but again the problem is that they are all manual, and they ask you to build actually a very big matrix, that how many tests did you run, what was your configuration, what did you get, how many passed, how many failed. No formal assurance at all. Everything is quantitative, numbers, no formal assurance, no argument coming out of that. So we build it according to the US federal strategy. We build the system right, and then we continuously monitor in order to make sure that it behaves always the same as it is required. So how do we do it? We actually certify that its design is correct first, when it is developed, like the design, model, implementation, and then its execution, same when it is running. So at both times, we make sure that its behavior is as was desired. How do we do it? We specify the behavior as functional and non-functional properties. So really, this is the software engineering approach. Functional properties are the properties which are related to its functionality, and non-functional, how much energy should it consume, what should be its performance, what should be its security requirement, right? And then we certify that its design is correct, and it meets the requirements through incremental refinements. And then when it executes, we have a tool, ARMIT, which monitors that the execution is also happening according to requirements, which we call specification. So the system behavior, little depth, is the following. It really, behavior is the computations which are happening in the computer and the data which it is exchanging with other components or with the network. So we are talking about the two behaviors. The computational things may go wrong, as we have seen the computational attacks, for example, Stuxnet was one of them. But then also on the other hand, we have these data attacks, right? Data integrity attacks, false data injection attacks, stealthy attacks. I mean, everything is about data. So here the data can go wrong. Your system is working fine, but the data I'm providing is wrong, right? But on the other hand, the computations also may go wrong. So we have to really secure both of them. That's how do we do. And as you can see, the program for us is the instructions. Each instruction is already operating on some internal data. Internal data is the data which is hard-coded in the program, right? So they are actually part of the instructions, which is the computations, and then is the input data which I'm accepting from the environment to perform computation on. So we really want to be secure at both ends, because they both can be attacked, right? By anyone. So we really want to make sure that the computations are safe, so that they terminate, they do not have any bug, they are compliant with any required regulation. And similarly, the external input data is also reliable. And here really we want to ask, do we believe that whatever we see is real? The data which I am accepting, how can I believe that the data is really real or the data is fake? So this is really a challenging problem which we have dealt with. And then actually it also leads to the question that data can be legal, but still it could not be real. For example, if you ask me that go to this wall, I can move on right, on left, on back, But when I'm given a goal that I have to reach this wall, then I can only move forward. So this is my legal move, right? I can still move on left and right, but they are not real moves. They are illegal in this sense. Why? Because then I will not be able to reach my goal. So here really the question is the data integrity threat. So as I said, that we certify that the computations go well with the help of proofs. And we also make sure that the external inputs are really consistent with respect to their properties. And we here apply the results from nonlinear verification, which was actually NP-hard problem, which was recently solved some few years ago. And then we also make sure that during the execution time, also the computations and the data is safe. Not only when we are developing, first we want to make sure that whatever we have developed, that is correct, that is secure. But then when we execute it, we also want to make sure and we monitor it that the execution is also happening correct. Whenever something goes wrong out of that, because still anything can go wrong. So, but we are able to detect it immediately. So for the implementation, how do we develop the software correct? This is essentially we use the abstract data type, which is actually a well-known concept in computer science. We start with a high-level specification. We add new information, and eventually we get one deterministic program. But at each level, we have a proof which makes sure that I am not inconsistent with my previous behavior. So at the end, every chain is consistent. Nothing new has been introduced, and it exactly does as it is supposed to. But then at the end, I will not have only a program, but I will also have a proof which will tell me that why does it do a certain job. And as I mentioned, we are really using here the COC, which is actually a proof assistant, where maybe those of you who are aware of it, the COC has actually a certified kernel in itself. So it has a language, which is actually a very small language, which is certified that it never produces anything wrong. So a small example, looking at the water tank, which is very simple to understand. Imagine that we have this water tank which actually accepts a command to fill some water, and it also drain some water. So the specification will look like the following thing. For example, I'm not sure if everyone can see that, but in box, you can see some code which is not like Java. For example, I can assign a variable a value n or true, which doesn't make sense, right? But this is how we actually refine the assignment. So it essentially says this procedure that whatever the value I get as a command, that for example, I give a command that fill this water tank to 7 meters. Okay. So should I accept this 7 as it is, or should I check that whether the command is consistent? Maybe it is already full. Yeah. Maybe it is already empty. Or maybe I have a wrong command. Do I need to check, or I can just accept anything? So this is exactly what it says. Should I accept some value, or should I just ignore it? And then when we refine it, at the end we will get this kind of code, which is really a Java code, yeah, where we say that at the moment, accept the reading as it is, we don't care. But then when we are going to perform operation, then we will make sure that whether the command is consistent with the current state of the system. For example, when already the water tank is full, I cannot ask him to make it more full, right? Similarly, when the water tank is already empty, I cannot say to make empty, right? So these kind of questions will already be handled when we have accepted the value, and then later when we develop the operations. So this is the big picture of the system, but which I am going to explain is actually in this box, red box. So essentially we have an implementation. You can have the design, but for us it's an implementation. Then we have its specification, that what it is supposed to do. So there is a program implementation, which is a source code. But then on the other hand, we have the specification, which is the requirement specification, what it should do. And then from them, we generate actually a synthesizer against the implementation, which observes this implementation on the fly during the execution time, provides me some data, and I actually compare that data during the execution at behavioral differential level. And whenever something goes wrong, I suspend the execution. I tell the diagnosis engine to diagnose what has really happened wrong, because everything is connected. I have the full data, I have the full specification. I can easily see whether some data has been compromised or some computation has been compromised or whether this is an attack. And then it tells me something after consulting with some other components, and it tries to recover into the safe state, because that's the requirement of industrial control system, that you cannot fail. You have to be fail safe. We also have backup data, so that if system wants to resume in one of the previous safe states, so that it has a data to resume from it. So just to give you a small demonstration, because this is what the example which I'm going to use, the same example which I've just shown you, the water tank example. So imagine that we have some water tank, but its design is very smart because it already has some drain in the ground. So it means that the attacker cannot precisely judge the current state of the water until he sees. So there is a pump which can fill in the water and can go out. So then we have this controller through which we are giving the commands, fill it or dry it. And this is the specification part. So we have written the specification of this whole process here. And then whatever is happening in the real time, we are comparing it with the specification. So we are maintaining its state, that what is the current state of the system. Whenever new commands arrive, we compare them, that is it the expected behavior or does it going to violate one of the properties. Whenever everything is good, we stay continue. Whenever something goes wrong, we alarm, and then the further processing goes. So for the demonstration purpose, as we have developed it in Lisp, and Lisp is actually a license tool. So we have then prepared the video just to show you these both kind of attacks again. One is the computational attack, when something within the instruction has been changed. So imagine that I am the guy who has developed the program. I have access to everything, right? I have access to the source code. If I change the code, should I be able to change? No, this doesn't allow. It will be cat. And similarly, if I get the wrong data, the program is fine, everything is fine, but I am giving it the wrong data. Should it accept it? No. This is what we say, it is well known anyway in security, the fast data injection attack. We are also able to detect that. So the insider attack is also covered, because insider is the very important attack. Imagine that at some point of time, the pilot of an aeroplane decides to kill everyone. Should he? No. System should not allow him to do that. So this is exactly what is going to help. So as you can see, the first attack is, we are going to set some of the parameters. You will see in the graph when the water tank will start overflowing. In the first case, it will overflow. Yeah, no one will be able to detect it because there is no monitoring. It is going to. Then we will enable our monitoring system, and then it will immediately detect that something has gone wrong. So this is the attack now. Just changing some values. And without monitoring, as you can see, it has overflown. No one was able to detect it because there is no such mechanism. Yeah, I can give him wrong command. It can do whatever it does. Now we are going to enable our monitoring system and going to ask the same command. As you see, immediately it detected the inconsistency between what is the current state and what it should not happen. So it has been set. And now we are going to run the other part, where some parameter is going to be changed, some parameter value of the, so imagine that some controller parameter is going to be changed, some inside. I was not able to detect because no monitoring is enabled. And now we are going to enable our monitoring. We will be able to detect it immediately when things are going to go against that, you see. When it was just crossing the borderline, we were able to detect it. So, and we have eventually concluded not only that, but we have also told you that why we were able to detect that. Actually, this was the value which was expected, and this is what we got, right? So there is a difference, and we were able to detect it immediately. So then just some few words about the framework. As I have told you that the system is self-aware. Why? Because everything is happening with the logical specification. In the logical specification, we at any point of time, we know what has really gone wrong, because Logical derivation has already its system which is sound, how to derive the new knowledge and how to predict certain things. And as I said, that system is allowed to behave only legally. There is no other way. Why? Because I have written everything in the specification, and now system cannot do anything wrong. And I have a proof for that when I have developed the system, that why a system will not behave illegally. And here, as I said, that we really make sure that everything which we have developed is the prediction. This is what system is supposed to do. At runtime, we collect the observations, which is the real-time behavior of the program. We compare both at runtime, and we see whether everything is consistent. If it is inconsistent, then the diagnosis engine is started to further investigate what has really gone wrong. And as I told you, that we are able to detect not only the known attacks, but also unknown attacks. So at the moment, I'm not going into the detail of the specification language which we have developed, but it essentially allows you to model anything what you can imagine about an attack, even the future attack, if you can think of. And the system will automatically be able to exploit that behavior to see whether the system has a certain vulnerability or certain attack possibility. System is adaptable. You can have new policies coming around. You can have new regulations coming around. Just add everything in the prediction and let's see whether the system behaves according to the same way. And more importantly, the system is sound and complete. Whenever there is an attack or an error, it will detect. And whenever it will detect something, there is definitely something has gone wrong, whether it is an error or it is an attack. So for the vulnerability analysis of the data, which is false data injection attacks, this is actually the class of stealthy attacks, which I have mentioned in the start, because your system is doing very fine. Your program is running good. Its behavior is correct, but actually it is operating on the wrong input data, right? So how to see that whether the data is incorrect? So here, this problem is really NP hard, and recently it has been solved by delta complete procedures, where we have now the tools which can be asked the following question. Given a system which may include some non-linear constraints which are continuous, yeah, you may want to ask it, does your program has some error, or does it have some properties, does it have some values which satisfy your model properties but they are not real? Right? So this is very critical, yeah. And if to give you some example, actually we do not have some, maybe we can write here. So just to give you an example of a small Java program, which actually adds two numbers, right? I have integer x and int y, and I just return x plus y. So do you think this program is correct? Just one liner. Adding of Java two integers, yeah? I'm adding two Java integers, just two parameters x and y, and returning x plus y. Of course, we have learned it in the first semester, yeah? But that's not correct. Because still there are some values for integers which are legal, which are in the range of Java integers, but for which I will get the wrong result. And this will particularly happen when your integer values will overflow. I can have the maximum value of x and y, and then I will have incorrect result. So these are the values which we can also ask for the existing system, but also when we are in the command and control system, industrial control system, we have maintained a certain state, we can ask whether the new values are really the real ones. And the system will bring us two answers. Either it will say, no, all the values, whatever I find, they are real values. There is no chance that I have illegal values. Or it will say, yes, there are some values. And for example, in this case, it can tell you that, yes, there are some values which are illegal. Why? For example, the highest values of x and y, which are going to make system overflow. Yeah? Then we know that for some values, this program does not behave. And then it is up to the designer. Either I am going to make the constraints more stronger, or I can detect those values on the runtime and then can decide what to do with it. Right? For example, in this case, there could be two solutions. One solution is that instead of changing the other parameters, I simply say that the return type of the procedure is long. In the long now, I can accept the maximum values of x and y, and then everything is perfect. But now I know, yeah, that what has gone wrong and what things which are there which I have changed. And then the constraints will be different. But now I know at least, right? So with this method, we are able to detect the stealthy attacks. And thanks to all other team members, me in Carinthia, Dimitrios is the director in Industrial System Institute in Greece, and Howard Schrob is the director in Cybersecurity Initiative at MIT. And there are some other collaborators which I want to thank. So this work has been developed in collaboration with it, and the paper has already been published in Proceedings of the IEEE. That's already out. You may want to see that. And finally, thanks to DeepSec for giving me the opportunity, and thanks everyone for coming and bearing with me.
Thank you.
So if you have any questions, we have some minutes before we leave for lunch.
Questions? No? No one?
Do you have any experience on how your method scales to bigger real-world problems?
So these two methods really scale as bigger as we can think of because of their...
I mean in practice, not theoretically.
Yeah, in practice at the moment, we are still looking for some real big scale application. So currently we are actually trying to find a couple of case studies. One is actually already going on with CERN, because CERN guys have the physics data where they have very huge physics experiment. Over there, we want to see whether there is data integrity is there. But for the other application, we have already tested it with the benchmarks of the industrial control systems, and our monitoring system is well adhered to the runtime requirements, the real-time requirements of the industrial control system. But of course, until we don't find the real big scale, we cannot argue whether exactly will it work. But at the moment, yes.
May I ask another question?
Sure, sure.
And how do you guarantee, how do you certify the correctness of the specification, which is also given in some language and can be buggy and faulty?
Yeah, that is a good question, in fact. But let me tell you, this procedure does not really allow you to have an incorrect specification in principle, until or unless the developer intentionally does this. Intention still we cannot guarantee, because human, if I decide to do something, of course, the whole room cannot stop me. I will do it. But in principle, when you are proving these things, during the proving, you will come to the process where you will really understand whether something is really incorrect or does it make sense. So in this whole process, it's not possible to really have a stupid specification coming out at here, until or unless the whole team wants to have something to go out. So this process doesn't allow it.
Is there a reason why you choose Coq to make the verification and not another SMT solver?
Yeah, that's also a good question. There are many reasons. So the first reason is actually that it already has a language, kernel language, in which we develop the proofs that is certified, which means that it does not accept anything incorrect. Whenever it tells you something that is really indeed a proof why it did that. Secondly, it has the proof tactics which are programmable. So once we have developed, I have proved something, then if you are going to do the same thing at some point of time, you do not need to do everything. So the library is there, you can use my tactics. So this is exactly the other way that, like, we develop the APIs nowadays, and we put it in open source. In future, we plan to put all these proving tactics open source so that anyone can reuse it. So these are the two main strengths.
Yeah, but like the C3 is also a verified language and use also SMT2, so it's the same language.
SMT is different than the proof assistant. So SMT does everything automatically. This does everything interactively. So human is in the loop here. This is the proof assistant, where human has to guide the proof. So We do not trust automatic thing. Yeah. Automatic things have their own problems. So I can put actually some references on the B log to help you to understand that what is really the difference between automated theorem proving and automatic theorem proving. So, yeah.